and there are more than 100 people who are engaged. So I tried to skim it together and give an overview of the carbon in nutrient responses so far to CO2 fertilization. And talking about carbon dioxide, so the left side is showing the human-induced sources of carbon dioxide going into the air, about 35 gigatons from fossils and about 4 to 5 gigatons, depending on different publications from land use change. Of that amount, 26% is taken by the oceans, 48% contributes to the increasing or the rising concentration of CO2 in the air. And then about 30% or 29 is taken by the land systems. And within the land systems, 18% is taken up by the forest itself. So it's a substantial sink there. With increasing atmospheric CO2 concentration, it is expected that the CO2 sink in the land ecosystems will increase. However, carbon dioxide is not the only controller of the fertilization effect or the stimulations of productivity. There are other factors, for example, nutrients or water availability, and how those nutrients might be constraining the response in terms of the CO2 fertilization effect. IPCC published in 2013 and then in 2019 the land carbon sinks response. And so I'm showing the latest one here. This is the land carbon sinks response. In the open circle shows the carbon only models in terms of CO2 fertilization effect. And then the carbon and nitrogen, when both are pulled together, so you see the dark filled circles here. And there is substantial uncertainty in terms of the CO2 fertilization sink being reduced by 25 to 67% when you account for nutrient availability. So it's highly uncertain. And particularly, this figure does not include any experimental data for mature forest types in the northern latitudes to start with. So what happens with the mature systems? The Birmingham Institute of Forest Research established a 3-year carbon enrichment facility in Staffordshire, where there are 3 ambient arrays in 3 phase treatments where the carbon dioxide concentrations are increased by 150 ppm above the ambient from dawn to dusk during the growing season. And then we have an additional 9 infrastructure controls as well. The details of these experimental setups are being available in these published work already. Fumigation started in 2017. It's going to continue up to the end of 2026. And with the start of the fumigations, and just before the fumigations, we started measurement of the various response variables, including carbon flows, nutrient responses, the ecology of the forest itself, the resilience and health aspects of these systems under elevated CO2 concentrations. Today, I will focus on the carbon in nutrient aspects of the responses. And talking about the responses, so above ground responses, initially with the startup of the CO2 fertilizations, the carbon uptake increased by an average of 23%, 2017, 2018 in the initial years of the phase fumigation period. At the same time, the leaf mass or the thickness increased as well substantially. And with this CO2 uptake, the trees' basal area increments on average increased by 28%. So more growth, even though these trees are 175 years old, they still have the capacity to grow more and more and more. When we converted the basal area increments into dry matter increments on a tree basis level, so on average from 2017 when the fumigation started up to 2022, we see stimulations or upregulations of the dry matter increments on a tree basis in kilograms, which is on average about 10.7% now. And there is year-to-year variations. You could see it in 2020 that we are exploring to know the reasons why it's happening. Probably the infestations in 2019, the moth infestations, which denuded the trees early on, might be one of the reasons for that. No response in 2020. Moving from 2018 in terms of the CO2 responses, even in 2022, the mature systems are still under elevated CO2 is taking up more carbon. So this uptick in the carbon uptake over time since the start of the fertilization experiment is continued by 2022, so on. Similarly, the litter fowl from over the years, and then from 2018 onwards, on the average increased under elevated CO2 arrays by about 14% on average. So more carbon being captured, more allocated to the increasing the girdle of the trees, but at the same time, the litter fowl amount that goes into the forest floor increased as well. Interestingly, at the same time, this figure shows the amount of nitrogen in the litter fowl. And from 2019 onwards, the amount of nitrogen that goes into the forest floor in the litter substantially decreased, meaning that the trees are reserving the nitrogen just before senescence, so that this nitrogen could be allocated to the buds next year for the nitrogen economy of the trees itself. So if we move on from above ground responses to below ground responses, what happens? In terms of carbon allocations, through years, we have seen that the fine root biomass, particularly in the upper soil horizons, have increased. I'm just showing data for 2021 and 2022 that we could see an increase in the fine root biomass. So again, more investment of the captured carbon going to the soil itself. With this more fine root biomass, there is also an upregulations by about 40% in terms of the exudation of carbon by the roots into the rhizosphere. So exudates are like a cocktail or a slush of palatable carbon that microbes could use to really decompose soil organic matter to allow them to seek nutrients, for example. So this is a priming of the rhizosphere to really vitalize the soil processes in search of nutrients. And that exudations increased by 40%. Interestingly, while the carbon exudation increased, the nitrogen in the exudation decreased because the nitrogen in the exudation stayed the same while the carbon went up. So not only in the litter pile, there is a strong evidence now that the trees are conserving nitrogens to be capturing carbon below ground. The exudations is also trying to save nitrogen and allow the carbon to be given to the microbes. This figure shows now what comes out of the soils when we have these microbial in root respiration processes. Initially, we saw an increase in the total soil respirations, but over time from 2020 and 2021, this effect is declining. This is one of the puzzles for us, and we're still wondering what's going on, whether it's the seeking of nutrients is much more efficient, whether the microbes are targeting nitrogen-rich compounds. So with the less respirations might still be able to deliver the amount. Something that we are thinking about, what is going on here. And that's important because when we look at the nitrogen in the soils, there is on average, when we did lab studies in 2018 to 2020, we see an increase consistently in gross nitrogen mineralization, which is the conversions of organic matter into nitrate and ammonium. These are the pools that are usually prepared by the trees and microbes to take up, particularly ammonium, where the turnover rate is quite faster than nitrate. So the supply of nitrogen has subsequently increased to the trees in the form of these mineral nitrogens, nitrate and ammonium here. So that's the work published recently this month. And then we continued with these gross mineralization studies. And again, when we move on from 2018 to 2020 to 2021 and 2022, we see a similar response of higher gross nitrogen mineralizations, meaning delivering more nitrogen into the soil available pool there. Now that more ammonia and there is faster turnover rates here, so it means maybe the trees are taking more ammonium, which is a preferred nutrient compared to nitrate. It's also a preferred nutrient by the microbes because if the soil is being enriched with a slushy material being delivered to the soil, the microbes population grows up, and if they grow, they need nitrogen together with carbon. And so this higher mineralizations, microbes might be doing it so that they could access the ammonium. And this is why the turnover of the ammonium is quite fast. Nitrate is slow. And as a nitrogen scientist, because the pH is low, the processes are suppressed. So it's a long whole story that I'm not going to get into it. But the nitrate here, the slow turnover rate is because the chemistry of the soil is such that everything is more focused on ammonium, and the conditions are not conducive for nitrate production. But if the ammonium is taken up more by microbes, and I'm not showing the data, but it is about 20% uptake in the uptake of ammonium in immobilization of that ammonium by the microbial populations in the soil itself. So that might be the reason we see more mineralization. The previous slide, I was showing data based on isotopic analyses. And now I'm showing data based on field mineralizations, non-isotopic methods. Both the release of ammonium and the release of nitrate in both processes. On average, it has gone up in the treatment rings. And if we use the data and calculate, these systems deliver about 25 kilograms of nitrogen per hectare per year as an available nitrogen pool to the trees. So it's a substantial amount being sourced from soil organic matter mainly to be available to microbes in trees. But when we looked at the trees, what the trees are munching upon in terms of the nitrogen, that was a completely astonishment to us. The first thing we saw is there is a 36% increase in root nitrogen uptake. That's the work came from Johanna's experiments last year. So fresh, but more importantly, this figure shows the uptake, the percent nitrogen uptake of the different nitrogen forms. So nitrate, ammonium, and amino acids. So I mean, amino acids or organic nitrogen. And then we did these uptake studies in the summer and in the autumn, and then under ambient conditions in elevated CO2. So fresh data, but overall, the oak roots pretty much took more than 80%, and at least 80% of the nitrogen in the form of amino acids rather than ammonium and nitrogen. So here, and previously people reported organic nitrogen uptake, but at a lower amount. That's what we see here. So it might be a strategy by the oak trees to really take amino acids because the trees might be competing for ammonium with the microbes, and the microbes might be mineralizing the soil organic matter. So it might be the interplay between microbes and trees trying to, these oak trees particularly trying to bypass what the microbes might be looking for. And that's what we see, but quite interesting to see this type of response. And maybe the associated mycorrhizae, the ectomycorrhizae, are probably the key drivers of this higher uptake preferences for organic nitrogen rather than ammonia. Our current global models mostly rely on input of nitrate and ammonium and total nitrogen. We don't account for these type of uptakes, and probably this is why we see higher uncertainty in these different levels of models when it comes to nitrogen and nutrient availability versus the CO2 fertilization effect. Try to conclude. So some key points in future research directions. First we see is that the mature trees, 175 years old, are able to grow and get more carbon. The next question is how long it's going to do it? Is this as an initial bump response and it's going to slow down? And there are always extreme events and more frequent than in the past. And Jason rightly referred to some of these changes happening more drastically. So what would happen to the carbon capture when there are more extreme events, whether it's going to augment it or suppress it? In general, long-term data, more than 10 years, in terms of the year-to-year variations in climate extremes and carbon capture under elevated CO2 is very poor. So we don't have much data in these areas. We are trying to capitalize on our decadal scale experiment to really unpick some of the additional factors like climate extremes of warming, soil moisture deficits, or drought, and how those might be affecting the carbon allocations and eventually the wood formations. But this also gives us an opportunity to think in a forward way and whether we might have the ability and capability to go beyond a decade and see how this response might turn out to be with reference to the extreme events that we see it from year to year now, much more frequently in terms of carbon. Same is nitrogen. Nitrogen is conserved both by resorptions and exudations. And at the same time, the trees are allocating more carbon below ground. And mineralization of the nitrogen and the supply of nitrogen in general have increased. And we also see and upregulations, we also see a higher uptake of organic nitrogen than we previously thought of. The key question is how long this nitrogen supply, 25 kilograms per hectare per year, could be sustained by soil organic matter, because this is not unlimited, it's a limited store. And there might be a point where we might bump into progressive nitrogen limitations, the phenomena that the systems don't have much of the available nitrogen to be feeding into the trees. So if we have faster mineralizations going on, and that's being captured in biomass overall, then in terrestrial systems, particularly in the temperate regions, we might be losing the stable soil carbon for gains in biomass carbon. And it's a trade-off. Stable soil carbon, which is for millennia and years, above ground biomass could be quite short term. So these are the questions that we would like to explore, and we will use our available resources to really fine tune what we see so far. So with this, I will thank all the funding bodies, and more importantly, a whole suite of researchers, particularly the early career researchers who generated this data. So it's not me up in the canopy, but either it's Carolina Mayoral, it's Johanna on the ground trying to unpick the roots without snapping it. So thanks to you all. It's been a pleasure working with you. And then the diversity of national and international collaborators that we work with at BIFoR-FACE. Thank you.
Thank you very much, Professor. We will continue now. Hello. We will continue. Okay, yeah, this is better. So our next speaker is going to be Professor Neil Loader from Swansea University.